Hey, welcome to week 6 of this course. Please sign in. Please be seated. We already have started. I want to mention a couple of logistical things before we go in the technical discussion tonight. The first one is your midterm exam. I want to invite everyone to pay close attention to the Discord postings, specifically about logistics, what you can do, what you cannot do, what you can bring, what you cannot bring in the midterm exam. There will be no excuses as to I did not know. Please read the document carefully and act accordingly. Prepare accordingly as well. I'm hearing also that the application that I was recommending for you to use to scan your answers, Microsoft Lens, has retired. I had no idea. Use any scanning application that is you double check is able to do two things: create PDF files and make sure that all the scans are coming into just one PDF file. Okay, that's the PDF file that you will upload in a Brightspace at the end of the midterm exam. Okay. Over here in the midterm study guide, there is a whole bunch of questions from previous exams. Similar type of questions you will be asked. Okay. Obviously, none of these questions will be asked. So I would suggest to go and take a look and start working on those questions on your own after you have a kind of a dry run on preparation kind of next week. And if time allows, next time we meet, we may go through some of these questions over here as a kind of a preparatory kind of step. If time allows, I need to finish certain things before I determine. So let's see how it goes tonight, and we'll see what we can do next week. Okay, any questions with respect to the midterm exam? Yes.
Is that week 8 we're going over and stuff? Could that be happening like
week 8?
Like the midterm?
What is going on? We are in over here. We are over here this week 6. Okay. So your obviously this week 8 will not happen, right? So it will be moved this thing downwards, right? But yeah, I need to change that thing to account for the meter. All right. So I will tell you next week what will be the scope of the meter. So the scope, it's safe to assume it's going to be everything from the beginning of this course until that specific point I will tell you. Okay. If I have time to go through a portion of week 7 next time or the whole thing, I do not know. Okay, but I'll tell you what will be the scope next week. All right. So another thing I want to mention that anyone who has accommodations and needs to take the exam in a special place, they need to open a ticket. They need to alert me to that. Okay. All right. Okay. So sounds good. So no questions. Assignment 3. I'm running a bit late on assignment 3, as you probably noticed. Most likely it will show up this weekend. Okay. And of course, I'll give you the 2 weeks to prepare for it. So, what we're going to do today, after reviewing last week also was kind of an online kind of course, so I'm going to do some kind of review on that. We are going to go into scene understanding, and more specifically today, we're going to start the discussion on object detection. And I think the whole course will be occupied by that. If I have time, I will start the probabilistic reasoning over time, which is obviously, as I told you, is associated with the output of object detection and further processing it. So it's kind of a natural kind of thing to follow. All right. Something else before I forget. I see the statistics of participation from across a very large class of people showing up in TA meetings, in TA Q&A sessions, help and things like that. The participation is very low. In fact, last time it was exactly 0. The previous time was 1. So 1 out of 60. The previous time was maybe 2. I think it's going to be a very missed opportunity if you don't take advantage of this resource. Okay, the university is paying these people to help you. As you also noticed in the assignment, sometimes you leave it always at the end, at the last minute, and then no one is there to help you. So be proactive and show up in this TA because these people, they have gone through this course many times, or at least 3 times. All right. So let's move to review. Of course. Okay, I'm just going to start with this thing over there, the essence, if you like, of the CNN kind of operation, and I'm going to ask a couple of questions. What are we trying to do with the CNNs? What are we trying to do with CNNs? Why we are suddenly we're interested in this kind of convolution operation? What are we trying to do with it? So we are trying first of all to do 2 things. We are trying to hunt for any correlations, right, that are present in a spatial domain. Okay, in an image, for example, right, you have some structure between the features of the image, and you're trying to extract information out of this structure. Okay. We are using, I will call it a special kind of thing, or we call it a filter, right? And this filter was 3 by 3, let's say, and had some kind of a depth that is processing the input. The input obviously will have a depth of 3 at the very beginning of the network, but in general, it can have a depth of ml-1. And then we discussed what is at any one instance in time, what this filter will do. At any one instance in time, there's going to be one and only one operation that the filter is doing, which is very familiar to us. That operation is that of the dot product. It's going to do a dot product between what? Between the filter, right? And the contents of the input feature map at that specific moment in time. Therefore, it will paint a scalar. Okay? It will determine a scalar we call Z. And the whole discussion there was, okay, as the filter kind of moves, the other scalar will be painted next to it, and next to it, and next to it. And under a day, we realized that the one filter is going over all possible locations that it can move to inside this input feature map to determine one slice of the output feature map. And this slice is the whatever matrix of pixels. And so how we are generating an output feature map of depth ML by using multiple filters. Okay, that is the answer. We're using multiple filters. And we also saw an animation. And I asked you to make sure you to understand that kind of. So we are effectively in the CNN operation, which is basically a linear and non-linear operation, what you see right here. Is it a linear or a non-linear operation? Right here. It is a linear operation, obviously, as you can see here from the expression to the right. Okay, and evidently, we will need to add a bias term, just like what we did at the output of every dot product that we have met in this class. And then after that, we will add also a nonlinearity, which continues to be a ReLU. And that is basically the conv whatever is called in Torch API for calling and defining a conv layer. All right. Then as an example of, we saw many kind of patterns of other kind of components of CNNs. And we also saw the residual kind of networks as well. And what was happening in these kind of residual networks? We were having an example here of three blocks. Inside F1, what should I see inside F1? Inside the ResNet, what should I see inside F1? Conv. We will see convolutions. We'll see obviously some form of, anyway, we haven't really touched upon batch normalization, some other kind of satellite components that are kind of quite important, and the time will come, we will discuss that. I may spend some time kind of see how progress I'm making, spend some time on this because we will need to use them, that knowledge when we are looking at transformers later on. So we'll see also some kind of ReLUs inside here. In any case, we are adding the input to the output. Okay, be careful with this kind of addition. It may not be straightforward. I think one exam I was asking you, go ahead and define and dimension this adder. Okay, in that kind of ResNet. Where do you go and find if your understanding is correct on that topic? Your Python textbook has a very nice section there on how to design this adder, right? With every single component that you need to design this addition. So obviously the number of dimensions here and the number of dimensions here are lined up, so you can do the addition, obviously. We cannot really cover every single architectural thing in this kind of lectures, but I'm just pointing out to places where you always need to review the overlapping sections of both the textbooks, both the AI, the modern approach, and the Python textbook if you want to do a good job in this class. Okay, so we wrote the whole ResNet of just three blocks as an equation, this long equation over here. And we redrew it later on, recognizing the fact that there are a couple of things that are worth kind of mentioning. The first is that while earlier with hard-to-skip connections, we only had one path to go through in terms of gradients. And someone asked the question, okay, what determines in that kind of path what will happen to the gradient? The backpropagation equations, which are the lookups that I was telling you about. And also, as the number of matrices involved in this kind of lookups, you will see that there is also the eigenstructure of these matrices also play a role as to what's going to happen. But that's kind of besides the point. Over here, we have a multiplicity of paths to go through in terms of gradient. And therefore, the gradient flow is greatly assisted. That was empirically seen and also shown evidently from the diagram. We don't have to empirically show it. And the second thing which is actually happening is that we have ensemble learning type of properties in the block diagram, in a sense that we are now considering the views of many different predictors create the prediction of the output of the ResNet. Very similar equation to the general equation of an ensemble learning. Ensemble learning, as I told you last time, comes with many names these days. Even in NLP, we will see later on some examples of that. Okay, so that was basically what we done last time. I think I cut short a little bit the lecture because of my excellent health. Believe it or not, this is the first time getting out of the house today. After I thought I recovered, the snowstorm came and I had to clean the driveway. 3 driveways, more specific. Anyway, so let's start. Whatever. This is now lecture 6. This is 227, 26. Whoever has the paper, please pass it around as I have to run this lecture. Okay, let's see where we are. How many things? All right, I'm going to start a discussion on scene understanding. And I'm going to just draw a block diagram. So we have a network of cameras over here. And we're using a capture device. These cameras transmit information over a protocol called RTSP, or real-time streaming protocol. So the system is kind of real-time. So these are transmitted typically with 30, let's say, frames per second. And over here, we are going to do develop a system where every single frame that is captured across the whole population of cameras is going to be fed into a number of pipelines. Over here, we're just going to be dealing with one pipeline, which is called an object detection pipeline. The output of these pipelines are, because it's video, constantly, every frame is coming constantly kind of in, is going to be published as a JSON stream into a topic of, let's say, a broker. A famous broker is Kafka. Another broker is RabbitMQ, whatever. The engineering aside, this doesn't really matter. But if you go for an interview in this kind of domain, I think you should know Kafka. You should know at least one broker to persuade these guys that you understand systems, right, to some degree. All right, so the image, I will pretend the image is right here. The image is coming in is this guy. And the output in the JSON, if you take the JSON contents and superpose it on top of the image, something which is not happening now, but it is it's part of the kind of engineering of, because in many instances, these streams are observed by humans, at least right now. I'm going to just blow up the image and I'm going to have, again, the guy with a prediction bounding box, which I will always have it as kind of this green box, colored green. And I'm going to highlight over here the way that I'm specifying the bounding box is the top left coordinate x, y, followed by h, b, and wb. Therefore, I need four numbers. Okay. And don't. This is obviously h, and this is w. Okay. So my y hat now, which I will specify here, is quite a long y hat. So it will have. By the way, I forgot to mention that I'm going to have also the class ID of the person who is bounding boxed, followed with some kind of confidence. So this is basically all the contents of the y hat. Class ID, confidence, comma, bounding box, X, Y, H, B, W, B. And I may have, a system over here is kind of trivial, but in reality, these systems are quite involved. For example, in an airport, there are around, in Newark Airport, there's a couple of thousand cameras in the security checkpoints, right? So if you go out of the country or whatever, traveling, and you look up, you will see lots of cameras kind of being involved. So we are talking about, if you do the calculation, I have some notes here, 2,500 times 30. We are looking at 75,000 frames per second as a kind of a payload which is coming into over here. Right? So some of these kind of facilities, they cannot really afford even to send the frames to the cloud, right? They have to have local compute for latency purposes, because obviously persons of interest need to be identified in real time. Almost real time. Okay, so The other thing, of course, which is actually happening is similar. Your assignment had to do with some form of similarity search. Huh? Yes. What was the assignment? I forgot, but it was something to do with similarity search, right? So a lot of these kind of boxes are further traveling down to hit vector databases of some sort and do similarity search against cataloged I guess a catalog of people that they need to talk to if they have been detected. Okay. All right. So that is the video surveillance kind of use case. And let's see some. However, we talked about object detection, but so this is basically what we will be building, right? We'll see this kind of pipeline, and we'll put all this kind of class of interest around the bounding box and confidence around its cutoff box. Okay. So it's kind of a trivial. The other thing that, of course, I want to mention here is that object detection, the bounding box, in other words, of object, is not the only task in scene understanding. We have a variety of what I will call satellite kind of tasks for this class, at least, called, for example, semantic segmentation is another one that requires not only for you to have, let's say, one component doing classification, another component giving you the bounding box, but it requires also a third component to see, okay, within this kind of whole scene, colored at the pixel level, the classes that are present. Why on earth we need this kind of resolution? Well, for a variety of applications, like in robotics, one of the main, as shown here by these two pictures at the bottom left, one of the main concerns of a robot, a moving kind of robot, is to understand the free space. Where can I go next? That's kind of a constant task. Obviously, if you bound box, if you imagine this kind of scene, and you put a bounding box around the space where the robot can, the free space where the robot can actually move, this bounding box will capture other cars, pedestrians, whatever, right? So we need a finer level of resolution for this application. Similar for medicine, we need a finer level of resolution to either count things or target things with lasers, so we kill only the bad cells and not the good ones. Okay. So for that reason, semantic segmentation is very much needed, and we have some and even further enhancements from semantic segmentation, which of course the end result here is to build polygons now. Within those polygons, every single pixel will be colored to be the class of interest. Let's say the class is chair, so all the chairs here will be blue. Okay. But obviously, you also need to have, in some applications, instant segmentation, like in the applications that we look at the surveillance, for example. If there was a camera here facing you, each one of you would have been colored differently, a different color, despite the fact that all of you belong to the class person. Okay, that's called instant segmentation. And of course, we have another further complication to that. Instant segmentation is great if you can limit it within, let's say, a single sensor. But in many applications, we have, of course, as we discussed, networks of sensors, right? We have a camera here in this room and a camera there outside. If I am identified with a unique color, therefore I am now possessing a unique identity because I am unique, and I walk out of this room, and suddenly I remember I forgot something and come back into this room, this identity has to come with me. I should not be counted as a new person, in other words, that enter the scene. Okay. This is actually quite important in sports analytics, where players, as they move around in and out of the scene, they need to be tracked. This is called, this of course requires, as I said, another layer of much higher layer than what is being considered here in this kind of single stage kind of pipelines, if I may call it. So in order for us to study even a simple object detector, we need data sets. So the data sets that we need are, a good example is the Microsoft COCO data set, which is actually a pretty difficult data set. And I think if there is one data set that you should know how to handle and manage is this. If there is one, this is it. If you can afford to know more, you can afford to know more. But if you are going to an interview, just make sure you understand exactly how to manage this data set, which has it's very popular, and therefore many companies even standardize data lakes around this format. So they work with a plethora of data sets, and sometimes they cannot afford to say, oh, this data set has this JSON structure in terms of ground truth. That data set has a completely different JSON structure in terms of ground truth. And so, okay, I cannot really work productively with like this. Therefore, I will standardize according to this sort of JSON structure, and therefore their MLOps becomes more streamlined, like operationalization. All right, so what we are seeing here is we're going to have an image, and we're going to see polygons inside this image associated with the classes. And obviously, this is an instant segmentation example, right? And this data set does not provide to us bounding boxes, like the ground truth bounding boxes, but any reasonable computer scientist can create a bounding box that surrounds a number of points in the two-dimensional space. So out of the polygon, we will create a bounding box if we need to. All right, let's take a look. I want to tell you a couple of things about that. Panoptic segmentation is another typical term that is used to color everything, right? Everything in this, including the background in some instances, right, of the images, which is background is kind of important. Some other tasks are okay. I forgot to mention let's take the person as an example. If it allows us to go there. Yes, okay, all right. So some things that are hidden also behind the image and the kind of polygons is this guys over here, okay, which is basically descriptions in natural language of what we are seeing in the image. Right? So this can be used for tasks like image captioning, and in general to train multimodal reasoning kind of pipelines, which is outside of the scope of this kind of class. This is where natural language processing, computer vision can come together. Okay, enough with the COCO data set. Except there was one that I wanted to, maybe this is called key points. Yeah. So in many kind of domains also, we're not really interested only for, this is another kind of task, but we're interested to plot or to determine, if you like, the sort of the key points around, if you like, an object, because behind the shape of these key points, there may be predictions. We can do predictions about the kinematic state of objects. So, for example, if you are looking at if you are a robot moving together with humans in this kind of scene, and you see a human standing, right, waiting for you to go, right? That's quite different than seeing the human in some kind of pose like this, where the person is running and trying to cross the road, for example. So lots of stuff that are not covered in this kind of course are behind this kind of data sets. And as I said, it's rich enough for you to cover a lot of stuff outside of the scope of this course later on. Okay. Oh, what happened? I was in some. Okay, I think I'm done with this website. So next time, the next thing I want to discuss is, okay, now that we know what we are going to build, at least we saw some outputs of what we're going to be building. I want to see for whatever shape and form this object detector takes, I want to study performance metrics. I want to look at some performance metrics to specifically the average precision, which is one of the many performance metrics. We have also average recall. If we understand average precision, we can understand many of the others. We cannot afford to mention everything. Okay, so I'm going to basically title this discussion now the object detection metrics. All right, so I'm going to present. Remember, in binary classification, we looked at various kind of events which are present. One of the events here will not be present. So let me show you what events will be present in object detection. So I'm going to have, again, the first type of event which is going to be present is I am going to have a prediction. And the ground truth bounding box in the data set will be called BGT. Prediction, obviously the prediction, the ground truth will contain the label. So is my predictor. Will give me a label. This type of event is obviously called true, positive, and I will symbolize it with a letter, with an index. I will index it with I because there will be plenty of those events, which I need to aggregate. All right, so TPI. Okay, then the second type of event I'm going to have is this event where I'm predicting that this is a person, but unfortunately it is a car, right? And this is obviously called false positive J. And the third event is this one. What should I call this event? What should I call this event? What should I call the event where I have no prediction? False negative sub k. False negative sub k. All right. So we are we have no true negatives in object detection. We are not interested to say this is not a water bottle. Okay, we are not interested. We are only interested to call out actual objects which are there. Okay, so no true negatives. Having said that, I will define now the first threshold, which is going to be important for determining, if you like, the value of the metric. That is going to be called the intersection over union, and the associated with it is going to be a threshold that I'm going to be using to characterize events which are going to be coming in. And now these events will be y hats, right? Okay, so over here I have another kind of image where I have the ground truth bounding box of this kind of class, and I have a prediction. All right, and I will define the intersection over union as the ratio between the area of B predicted intersecting with B GT divided by the area of B predicted union B GT. Okay. And so the obviously we understand that the IOU from this discussion is between 0 and 1. It is 0, obviously, if the two boxes are completely away from each other. And of course, it's 1 when the bounding box and the predicted bounding boxes and the ground truth are coinciding. So we'll be using now a threshold that we'll call small letter t. And I will write it over here as the IOU threshold. That will create one complication for us in the sense that it will increment a counter that is not a desirable counter. If IOU for every y hat is greater than t, then I will characterize the event as true positive. However, if the IOU is less than t, I will characterize the event as false positive, even if the classifier got the class correct. That's the important thing to understand. Even if the classifier got the class correct, it's a false positive event as far as the count increments are concerned. Typically, T belongs in a set of 0.5, 0.75, whatever. Whatever the value is, the data set where you are gauging your object detector against is going to tell you. So when you are benchmarking, that number is going to be there in the benchmark specification. If you go to the COCO competition, there are results for the specific T, the IU threshold, because obviously the stricter the T becomes, the some of the metrics will suffer. Is everyone following what the IU threshold is doing? Now that we have the IU kind of threshold, we can actually, because we already knew the confidence threshold from the binary classification days, I'm not going to spend any time on it, but I need to go back to that probability distribution kind of diagrams and ask you a couple of questions about that. I'm going to draw a block diagram that processes the y hat. Takes it through the IOU thresholding, which obviously T is a parameter. And then we have two options here. The first option is the IOU is greater than T. And the second option is the IOU be less than T. And in the first option, the true positive event will increment a counter called NEP. And because that counter is, the characterization of the true positive is a function of T, I'm entitled to write it NTP of T. Okay, as the frames are coming in, this counter will increase, decrease, whatever. The same thing happens for the other branch, FPJ and FP of T. Another counter I'm using for false positives. Then the two will go through a confidence thresholding that accepts the parameter tau as the parameter, right? The tau is going to be now the name of the confidence threshold. In the binary classification days, I think I called it W. I told you though I shouldn't have called it W, I think, because of the inherent confusion to the parameters of the classifier. But anyway, whatever the letter is, it is the one that I drew. I will show you in a moment because we use this kind of diagram. Evidently, remember that I had also false negatives that are incrementing the Fn, NFN. This NFN obviously is not a function of T. Why? Because I don't have a prediction for false negatives. It's not a function of T. There's no IOU for the false negatives to calculate. All right, so we have NTP then, of T comma tau. We have then NFP of T comma tau. And then we have NFN of tau. So the question that I need to ask now is the following. If someone asks you, as a function of tau, what would you say the trend of NTP is? Think. Is it increasing or decreasing? As a function of tau. As the tau becomes stricter and stricter, what do you think is going to happen to the characterizations of true positive events? Decreasing. Ever. Decreasing. What about the NFP? Decreasing. Why? Where is the binary classifier? Must be in your notes. This diagram here. Let's remember. What was the orange? Orange was orange state. Was how do you figure out, right? So anything to the right of the threshold, right? I'm calling it a positive. I'm calling out prediction to be positive. Anything to the left, I'm calling it to be negative. That's what we said. It's a binary classifier, right? So the area, the X belongs to the region R1, right? But we are wrong. So the left tail is the right tail of this guy. Right? So this one is false positive. The orange is a false positive. The summation of the green and the magenta was a false negative. As the theta, as the tau now, I call this tau the threshold, becomes stricter and stricter, larger and larger, what happens to the false positives? Well, follow the curve. It's reduced. That's why the curve is going down. Did we establish, though, that when the false positives go down, what happens to the false negatives? Are going down or up? They go up. So Wait, come back. Okay, so because it's a trade-off. All right, so we will use this kind of trends now to kind of create a story about, first of all, let me just write down what is a good detector, right? So a good detector, in fact, the ultimate kind of detector I can build, can pick up all available ground truths while avoiding to detect irrelevant objects. Pick up all available ground truths means what? What counter should be zero? NFN should be zero. Because only when NFN is zero, only then we catch every single person in the scene. Okay. Otherwise, we missed it, as you can see. Be very careful with these terminologies because they are key to understand, a lot of things in the object detection. So the avoiding to detect irrelevant objects, obviously now it's easier. It's an easier question. NFP should be zero. So with that kind of in mind, let's write down the equation for precision. Which is, if you remember, the summation from I is equal to 1 to n tp of tpi of t comma tau divided by summation from I is equal to 1 to n tp tpi of t comma tau plus summation of all false positives, which is obviously is a function, this counter of this quantity of both IOU and confidence threshold. Instead of writing from j is equal to 1 to n fp, I'm going to define here a quantity called number of detections. What should I equate the number of detections to be if I show you these three images, these three types of events? Summation of NTP and NFP. Only then I have a detection. Whatever the detection is. So I can write NTP plus NFP. Okay, I hope everyone is following. So I will write the NFP then as number of detections minus NTP. So I will also consider to be recall. The equation of recall is summation from I is equal to 1 to n tp, tpi of t comma tau. Again, the same thing. I is equal to 1 to ntp, tpi of t comma tau plus. Now we have from k is equal to 1 to nfn of fn sub k of tau. That is the formula. Let me define another counter called NGT as number of ground truths for the class of interest. Again, by looking at these three possibilities, what is the number of ground truths for the class of interest? Number of ground truths for the class of interest. The class of interest is obviously the person here, right? So the number of ground truths is NTP plus NFN. If you add the true positives and the false negatives, you told me this counter will be called NGT, but I claim that this count NGT suddenly became independent of tau, despite the fact that this guy is dependent of tau, and this guy is also dependent. And the question to you is why? And the answer is in this. So remember, we have NTP plus NFN. Do you see that? Do you see the answer? The answer always lies in characterizing the areas under the two probability distributions. We already have shaded the NFP, which is the orange, and we also have shaded the NFN, which is the green and the magenta. That's what you told me. So to answer the question, you need to understand where the true positive is. Because we're adding true positives and false negatives. This is the true positive. This area is the true positives. This is the area of false negatives. And this is the area of true positives. The summation of the true positives and the false negatives is the whole probability distribution. Does the whole probability distribution, the summation, depends on the threshold in any way? And the answer is no. And therefore, that's why the tau goes out of the way. And the only thing that remains is the t, the dependency on the IOU. So this has some significant consequences for us, that is, on the behavior of recall versus tau. Because now the only dependency is in the numerator, and therefore I can be entitled to claim this dependency. Inherited the dependency of true positives, in other words, as far as recall is concerned. I hope you're following. Things are all visual at this point. However, if you were to plot the precision versus tau. Can you make the same argument? And the answer is unfortunately no. And this is the reason, by the way, why in many textbooks you see this zigzag situation of precision and recall curves versus recall curves. This is the reason. The precision, in other words, has both tau dependency in the numerator and denominator. So as you change tau, you can be anywhere. So the precision has a kind of fairly noisy. Don't take this, what I'm drawing right now, for anything accurate here, right? I'm just telling you there's going to be something quite noisy in terms of its relationship to tau, which of course, if you bring the two together, because both of them depend on tau, if you plot them now together, you will come up with the precision recall curve. Obviously, these two quantities have maximum values of 1, right? But because of this situation of the precision, it is going to be a curve which is fairly zigzaggy kind of thing. If you see the example in the website, I'll show you in a moment. I'm not going to go through it because it's very numeric, but it's a good example to go through yourselves in order to persuade you that this is the situation. So ideally, I wanted to have an area under the curve that equals to 1.0, but I cannot. So the area under the curve, or precision recall curve, is the metric that I would be calling average precision. Average precision because it is the one that is average over all possible values of the threshold. And however, in the literature and in this benchmarking, we do not calculate this specific area, but what we do is we try to create some kind of a monotonic version of this curve with zero order interpolation. Some kind of interpolation filter is there to take this and make it something like this and measure this area and report it as the average precision. The area under the curve. And this is basically a number between less than 1 you need to report. How your detector, with all its properties, resulted into a stream of false positives, false negatives, and true positives, ended up giving you a number for this specific class, obviously. And if you have lots and lots of classes, they have also what is called the mean average precision. There's another metric called mean average precision, which looks like a repetition, but the mean is the average across all classes. So if I have a COCO data set with, let's say, 80 classes, I have a mean average precision symbolized by smaller than MAP, which is basically the sample mean of all average precision. Now, you need to be very careful because this number sometimes is used for people to say, okay, that detector is better than the other one, and then take this detector and they apply to their own kind of use case that supposedly has only a very small relationship to the data set that benchmark happened. So even within, let's say, a data set, you have significant class imbalance. A lot of people, very small number, much smaller number of ties for men. I'm just giving one of the classes of the data. Many more people though. So lots of classes dominate completely this kind of number. And some other classes which are less represented have very bad per class average precision. So look always at the histogram of average precisions before you select your detector which is appropriate for your use case. Yes, go ahead.
You would want to take the precision, you take the mean over the ith precision, right?
You take the mean over of the average precision, yes.
But average precision of every single of the ith class, right?
Of the classes, yes.
Why does it say precision of the kth class only? Why are we only adding?
No, this is capital K, the number of classes.
Right, but AP underscore I.
Small letter K.
Okay.
Which is the average precision of the specific kth class.
So what's the point of the running index I?
Is to calculate the sample mean. So if I have average precision for person something, another average precision for another class something else, I'm summing over all of these average precisions to calculate the mean average precision. And I'm reporting one number. Well, obviously I will report 80 numbers, right? Each class will have its own kind of average precision. I will report those as mean average precision, one number for the whole data set.
Right, but right now you're just adding the average precision of just one class, K times, and then dividing by K.
I'm sorry, your point is technical. Your point is this.
Right.
Okay, that's fine. Yeah.
Okay.
It was a typo. Small letter K. So the average precision metric is what you will always be reporting. Now, you don't have to do these calculations, obviously, because behind every framework, there is a dot metrics kind of API to support you in reporting all this kind of stuff. Now, however, over here, I have kind of a small example, which is worth going through at your own kind of pace. There is some kind of a small number of kind of images with their predictions and the kind of corresponding kind of ground truths. And we are going and calculating the way that this average precision is obtained as a kind of a metric, including plots that are associated with, as I told you, the interpolated kind of version, where you can actually see what we discussed earlier as the kind of a zigzagging going on between the two. Precision recall kind of curve, and then this basically the interpolated kind of version. Under this kind of area, you will calculate and report the average precision. It's worth, no one is going to ask you to calculate this kind of stuff, right, in an exam kind of setting. But if you want to have an idea of what's really happening in a small example, go ahead and do that. But someone may ask you about metrics, detection metrics. Just make sure that we don't take this to the limit, okay? All right, so with that now said, what we are going to do now next is, just like earlier, we've seen the metrics, now we will start looking at object detectors, kind of block diagrams. Now, I should warn you, the discussion on object detection is a bit block diagrammy oriented, okay? Behind every page that I have, we're going to go through 3 versions of an object detector. There is a paper. Okay? Sometimes these papers are like 20 pages long. Okay? And in fact, these papers are quite involved. There's a lot of engineering. I'm going to sample some important points that I want to mention and move on. Okay? Now, these days, there are 2 types of object detectors that should be used. That are not should be used, but they are used. The first kind of type is the so-called single-stage detectors. One classic example of that is the YOLO family that continues to evolve. The YOLO family, which your assignment was on that. I told you to use YOLO. The reason I told you to use YOLO is that this specific kind of company is make it very easy for you without really understanding what is an object detector, just use it. Having said that, you need to be very careful. Do not take YOLO as like the best thing since sliced bread because they have changed the licensing. Okay, so if you take this YOLO and try to deploy it somewhere in your own kind of company, the lawyers will knock your door on one day. Okay, so make sure you check the licensing and what version you can use, because I think after version 8 or 11, I can't remember now, they changed the licensing scheme. You have to pay them some money. The second category, which we'll deal with it today, is a category that's called two-stage detectors, and we need to understand why the two stages are kind of needed. Typically, and again, typically, they were buying us accuracy and they were trading us with latency. Okay. They were more accurate at the expense of latency. So in some kind of industries, they were preferred to do that. And initially, at least, single-stage detectors find themselves in a fortunate situation to be deployable in very small edge devices, as we call them, because they're quite far more efficient. There are crossover points, however, these days. This is not a universal statement, but this was basically the historical perspective, so to speak. Okay, so I'm going to start with the region-based object detector and see how that goes. Okay. So I'm going to basically showcase some kind of a scene over here, whatever. There's a table of some sort and a person. And the first thing that is actually happening is we are going to be segmenting the image into 1 million segments. So the first step is like segmentation. And segmentation is going to done using a graph abstraction. A graph obviously has some kind of set of vertices and some set of edges. Vertices you can consider to be the pixels and edges are weighted, connect the pixels, and they are connecting them with some kind of weighting according to a similarity metric. Okay, so for example, the simplest possible similarity metric you can think of is light intensity. Okay. I have an example over here. So let me know what the segmentation is doing a bit more formally. A segmentation S is the partitioning of V, of the set V, into segments such that each segment corresponds to a group of pixels that have high similarity. State the obvious. Okay, so for example, if this was the input kind of image, the result of that segmentation could be something like this. Mind you, there is no semantic association with anything here. I mean, this leg of the athlete is purple, this leg of the athlete is purple, but also green, whatever. The only thing we look at is some feature similarity based on some color, light intensity, whatever you can think of. Okay, you can bundle in that kind of similarity metric, various kind of features, and more importantly, the number of segments over here can be quite significant. A very, very large number of segments, and therefore we use a non-differentiable algorithm, and I'm calling it non-differentiable. You can hear me many times mention this kind of term today for a reason. A non-differentiable algorithm that cannot be implemented with, cannot be backpropagated. Okay? A non-differentiable algorithm, which I do not want you to get to know because ultimately it will be replaced with a differentiable kind of algorithm, called hierarchical kind of grouping. Okay, so with this kind of algorithm, we look at the various segments and we incrementally start merging segments now that as a whole have stronger similarity than others. Okay, so gradually we're going from a very large population of segments to some population of segments behind which we claim that there is an object. We don't care about its class. The only thing that this thing is doing for us is we claim there is an object behind it. We don't care. This is stage number one, which results into bounding boxes called proposals, which is a key term. We have a hypothesis that this segment and its corresponding kind of bounding box, there is an object behind it. Send it off to the second stage to figure it out. All I do as a second stage is provide proposals. So conceptually, it's a very simple kind of algorithm. And proposals will also be, obviously, depending on the segment, of various sizes. So it could be many overlaps with these proposals. In fact, in the first generation of the object detector that we call as region-based CNN kind of detector, we are going to have 2,000 of those proposals per image. So we have the following now things to do. Okay. Obviously, we now have 2,000 proposals. What are we going to do with them? Well, we are going to evaluate it. We are now we need, if you like, something that will represent each proposal as a vector, right? As a feature. So we need a featureizer. We need, in other words, a CNN to evaluate the proposal. So we're hitting these 2,000 proposals with CNNs, with 2,000 CNNs to give us some vectors at the output, right? And these vectors are going to end up being processed by, at a time, non-differentiable, again, algorithms for classification and regression. So, at this original kind of family of object detectors, we were, let me just show you this kind of image over here. We were having two non-differentiable components. One is a proposal generator, and the second was, okay, now for this proposal, I can tell you there is in fact an object with some specific class behind it, and here is the corresponding bounding box of that object. So the task of classification, we will understand it. The class of regression, we should also understand it because we did it. And in fact, I told you regression is going to come in as a task in object detection. Effectively, the determination of the four numbers, X, Y, W, and H of the predicted bounding box is a regression problem. We can treat these pixels, despite the fact that pixels are integer numbers, right? We can, of course, effectively, they're semantically, they are floating point numbers. They have nothing to do with classes here, the pixels of the tree. So, okay, so we have lots and lots of proposals, therefore, lots of determinations at the end to say, oh, there is a bounding box. This is my prediction bounding box. Oh, next to it, there may well be another prediction bounding box from another guy over here, whose proposal has highly overlapped with the previous kind of proposal. So we need something at the end to filter out all of these bounding boxes that we have already. And this algorithm that filters this out is called non-max suppression algorithm and survives to this date. So although many of the components we have seen are going to be replaced at the end, the concept of a proposal and the non-max suppression algorithm remain. So I'm going to spend some time now discussing this non-max suppression algorithm, how it is done, how we are filtering out to come up with the final predictions for our objects. And then I'm going to start replacing certain components to reach the final kind of block diagram, which I'm going to stay for a while then. Okay, so let's write down the so-called, so over here, there is some kind of discussion about, thousands of proposals are sent to the second stage for classification and regression. Okay. So put this kind of in a parenthesis. At the end, and this is basically something that will happen. I mean, training is done, right? I have trained, if you like, the elements of the object detector to correctly classify and to do regression or whatever that is for each and every of the proposals sent. During inference, now I have a trained kind of object detector who is going to spit up many predictions. I need to now have the NMS, the non-max suppression algorithm, to filter these predictions out. That's what I'm discussing right now. So non-max suppression. And this is basically survives to this date as an algorithm. So you need to know it. You need to understand. So first of all, applied rather during inference to filter out redundant predicted bounding boxes. Now, how this is done? The detector outputs, say, the BI spread and CI, K for each class K present in the frame, where C is not a threshold, but a confidence. Here's your bounding box. I'm predicting there is a car and get another bounding box. Like immediately next to it, you can think there's an image over there. And yet another one. Think about this green now. The color is a little bit unfortunate, but these are all the green predicted bounding boxes. So we need to go from here to here. Okay, that's what I'm discussing right now. All of these bounding boxes, again, are present during inference because I have now a trained, like what you did in your assignment. I have a trained object detector, and I'm having this. What you see, by the way, in your assignment is after the application of non-max suppression. You got a bounding box after the application of non-max suppression. I'm discussing now how the final filtering during inference is done. Okay. All right, so the detector outputs a whole bunch of bounding boxes and associated kind of confidence. So I'm starting now. For each class, sub K, collect all boxes with Ci, K greater than tau. This tau is a different hyperparameter compared to the tau we met for the mean AP calculation, the average precision calculation. It's a hyperparameter. In fact, behind every detector, there is like 100 hyperparameters. And many hyperparameters, not just one or two, we have many hyperparameters. And this is the reason why no one is these days starting to develop an object detector, let's say from scratch, right? But it basically they say, okay, I have an object detector, I know it kind of works. Let me adapt it to the domain, to my domain kind of thing. Adapt it as a block diagram. We inherit lots of hyperparameters. And so if your object detector is for this kind of classes and it has been developed, let's say, give you a real kind of example. You pick up an object detector from YOLO, from Ultralytics, right? And you try to apply it to anomaly detection in manufacturing, okay? And this object detector in Ultralytics, as we'll see a little bit later, it's also present in two-stage detectors, is trained to do multi-scale, to accommodate multiple scales, right? During the train. In other words, is able to detect U that you see in the first line of desks here, but also very capable of detect U that you're sitting at the very end of this kind of class. Right? Well, in manufacturing, in anomaly detection, the thing is right here. And the production line is like this, like thousands of widgets are going through the camera. You don't need a multi-scale detection. Well, guess what? You are inheriting this, and you are inheriting a whole bunch of hyperparameters who are going to completely screw up your anomaly detector if you use it as is. So there's a lot of effort to make it, to adapt it for the use case, even to the case where you need to start doing things that are a little bit Wild West stuff. Okay, so we why I'm mentioning all this, I have no idea, but I'm in this non-max suppression discussion. Collect all boxes with. Oh yes, I remember. I mentioned this because of this hyperparameter thing. This is different. It's yet another, it's NMS hyperparameter. So I'm collecting this that I exceed the threshold. NMS threshold. Okay. Sort the boxes that survive the previous comparison according in the descending order. Okay, and pick the B star, let me call it the B star, which is basically the highest possible in this descending order, row number 1, okay, which is the one that has the highest, obviously, confidence, right? Pick the B star and add it to the set of final detectors, final detections. Suppress all boxes that have IOU greater than another threshold T that again is specific to NMS. Okay. That have IU greater than T with respect to the B star. Are you following? So I'm filtering out, I'm suppressing everyone who has great overlap with my B star. I'm filtering out these guys. Yes.
What if the other boxes belong to some other class?
This is for class, for each class. I'm still in the each for class loop. However, I may have a person here in this frame, and I have another person over there. Obviously, I'm not going to throw the bounding boxes of this other person in the scene because of the IOU is not going to be greater than T, this other box over there. But I'm going to get rid of like in the car image that I showed you earlier, the ones that have significant overlap. Now, we need to be very careful here because in many use cases in computer vision, you are counting people. Lots of use cases like this, counting people. So lots of people people counting stuff are need to tune quite significantly this kind of threshold. So you don't get rid of the bounding box with the person sitting next to you. This is a different person. Yeah. The appraisal boxes that have a U greater than T with respect to the B pred. And repeat the process on the reduced set until no candidates remain. Candidates, in other words, that can be added in the final detections. And that's how you doing it on a per class basis as is set over there. You finish across all classes that you have. Of course, classes that have presence in the frame, right? And this is basically the non-max suppression kind of algorithm that's how you publish your final prediction. Now, there are some detectors these days called DETR or DETR, right? That do not have NMS. However, many do. Okay, but yeah.
Can you explain about
I am not going to explain it because we are never going to. Whoever mentioned support vector machine in this class? No one. I didn't even mention SVM. I can explain, of course, but it's one of the others that we are going to now replace. Right now, we're going to replace it. It is an algorithm, which, by the way, Vapnik, coincidentally, or not Vapnik. What is this guy's name? I'm forgetting the name. It's a German name. I'm forgetting. But anyway, invented, and it's a very good algorithm before neural networks came into the picture. and it is actually based on some nonlinear optimization theory of max margin optimization theory, as they call it. But we are never going to do that in this class. We are going to replace it with a neural network, with a classification head based on the dense layer, right now, in fact. So provided we understood the non-max suppression, we are going now to go into the second instance of this object detector, object detection kind of business, called faster CNN. And why we went into faster CNN, why the previous object detector was not good, it was good, however, it was so slow that no one was able to use it, because guess what? These 2,000 invocations of CNNs, in order for you to be able to see what is behind a proposal or not, took, of course, their time. And what we are doing with the faster CNN, we're trying to get rid of this. However, we don't get rid of this proposal generator. Stage one remains as is. Stage one remains as is. The segmentation, what was called the hierarchical grouping, all of this remains. Now we have proposals. However, these proposals are now at the pixel level, and someone thought, hey, why don't we go and take the whole image, pass it through a CNN, backbone, whatever that is, and map the proposal's pixel level coordinates to feature in the feature space, in the output feature map, which has been created out of this CNN. And obviously, you can understand this mapping is deterministic. Just like what I was telling you that, the dimensioning of the output feature map last time, right, is dependent on the stride, the padding, the whatever, the stride, padding, and what? Dilution, and the kernel size, obviously, we are able to do that here. That we can take the coordinate, okay, this pixel, where is it in the feature space did it map itself after all these kind of reductions, right? So anyway, so we are sort of suggesting that we will end up with some regions of interest, as we call them, in the feature space, these kind of proposals. And we need to take the regions of interest and pass them through now differentiable, dense, in other words, classification and regression heads to make a determination in this second stage as to what kind of class is this there or not. And this is basically what you see in the diagram. There is a pooling kind of layer that kind of harmonizes all the various kind of sizes of these regions of interest into one. And then, as you can see, there is a fully connected layers which are involved in the classification and regression. So no SVM anymore, and no linear regressions anymore are happening. And we are effectively have now a much faster object detector. That's basically what we have achieved. However, training of this still cannot be done end-to-end. Because why? Because the proposals are generated by an externality, by an external kind of algorithm, right? So we need to, the third and final sort of version of this kind of object detector is the one that we are going to spend time on. It's exactly identical to what's happening here, except that now we need to replace the hierarchical grouping with a neural network. Okay, and that's the final version. A lot of details. I don't want you to read this as if you are. I mean, the concepts are here. I mean, they're all the same. Yes, we are training it with. Obviously, you will see the composite loss very similar to what we see in a regularization discussion, where we have something to do with classification and something to do with the regression. I'll explain some of that as I'm presenting the third and final version of this algorithm. So this final version, which I'm going to spend some time on, is called, so over here we have this faster CNN. but I'm going to spend some time specifically on what's called faster RCNN, and more specifically on the what's called the region, the RPN. Okay, so I want to spend a few moments on explaining the need for multi-stage, multi-scale detection. Multi-scale detection. So we have obviously three possibilities. The third one is what we'll adopt over here. And one option is to say, okay, I have, as I told you, multi-scale detection is a requirement for many tasks where I need to have, to not have a catastrophic situation where far away objects are kind of completely undetected and the close by objects are detected perfectly. So I need to basically train the object detection during the training kind of exercise to see multiple scales of images of the same version of this object. So one way to do it, as you can imagine, is to feed it with scales like height and width. Over here, I'm going to have the h over 2 and w over 2. And I'm going to keep the filters constant to 3 by 3, let's say. And that's basically option one. Another option, which is equivalent, is to say, okay, I'm not going to scale the images themselves, but what I'm going to do is I'm going to scale the filters. I'm not going to do it right now, because I don't have space. But this filter here, instead of 3 by 3, is now 9 by 9. This is it's actually an equivalent version of the option number one, because effectively what I'm saying, I'm adjusting the receptive field that I'm hitting the images with. And I hope you remember what was a receptive field. What is a receptive field? The receptive field is the number of pixels. The number of pixels. Each of these pixels is affected by how many pixels in the lower layer? 3 by 3, right? But each of these pixels, they are colored in a layer below it by another filter called, that is also 3 by 3, right? And therefore, effectively, each of these pixels in this layer, relative to the feature map which I have not drawn, has a receptive field of 9 by 9. And as the network becomes deeper and deeper and deeper, each of these pixels of a feature map at the very end has now been affected effectively by a much larger number of pixels of the input image, right? This is called the effective receptive field of what is. So when I said receptive field over here, I'm suggesting that, hey, by adjusting the receptive field effectively, I'm buying multi-scale detection capability. So while before only 3 pixels affecting the pixel, now 9 by 9 pixels affecting the pixel. Right? So I have plenty of this kind of sizes to buy this equivalent situation to option number one. So option 3 is what we will adopt here. Option 3 is what is being adopted by this kind of faster RCNN version. And this is called the pyramid of anchors. Again, I am not discussing the object detector in general. I'm discussing the replacement of the hierarchical grouping algorithm with a neural network. I'm designing now a neural network whose ability is gauged on the fact to propose things that behind here in this region, there is this object and that object and that object and that object. I don't care what the class is. Okay, so that's the thing to remember. So pyramid of anchors is going to I'm going to define a raster of pixels. This could be pretty dense. And behind each pixel, I am going to, let's take, let's create another row here. Because, okay, behind, let's say this pixel, I'm defining a bounding box that I'll call an anchor that has some kind of scale and has some aspect ratio. Okay. So one scale, second scale, one aspect ratio, another aspect ratio, and so on. These are called anchors. Also known as priors. And I'm going to be defining, let's say 9 anchors. Let's say define. Let me write down. Define K anchors, boxes in other words, of various scales and aspect ratios. Let's say 3 scales, 3 ratios is raised to small letter k is equal to 9 anchors per position. 9 anchors will be here, centered here, another 9 anchors over there, and so on and so on. So I'm creating some kind of a sliding mechanism where I'm sliding these anchors across this whole image. So define a sliding window that for each location we produce a vector of features I'll explain that in a moment how we produce a vector of features. So we are so the RPN is designed, this network that produces this vector of features is designed to address one, is there an object behind the JF anchor? Yeah, that's question number 1. And if there is, to implement regress on relative coordinates of the anchor to the ground truth bounding box. So there's a lot of stuff going on. So let me explain what's happening. I am going to receive this image X. So first of all, the big picture. The big picture is the following. And then we go. This is the big picture. So I'm maintaining what I was doing in faster CNN with this CNN globally, right? Sees the image. But I'm producing now two paths, right? I'm diverting into the RPN in order for me to find out the proposals. And then for each proposal, I'm throwing it in the second kind of stage, which is untouched, to evaluate them. So what I'm discussing right now is this guy over here. That's the only thing that kind of changed. So obviously, there are some design and some kind of engineering behind the RPN, the details of which are in the paper. But if I am to draw a greatly simplified kind of block diagram of the RPN, I will see the following. I will see some X coming in. There will be a number of layers of convolutional nature, that is. Some of these layers will be shared with the main branch, the main kind of CNN. But bottom line is that for each of these kind of anchors, because now I know these anchors, I am constructing them anyway where they are, right? I will produce a feature vector that I will feed to a classification and regression head in order for me to come up with a determination as to is behind the JF anchor an object. Therefore, I need, if I have K anchors, I need K results here. Is an object or background? An object or background for each of the K anchors, 9 in this case. And obviously, if there is an object, I need the 4 numbers of my proposal. Therefore, I see 4 times K numbers being produced here because I'm producing numbers potentially for K anchors. Proposals that corresponds to, so each anchor could be a proposal, in other words. Could be a proposal. I do not know right now, but that's the number that that it makes sense for us to have there. So in order to train a neural network to classify effectively the objectness of something, right, that is in the scene, I need a training data. And the training data is the second stage of processing here in the RPN, of discussion, this kind of RPN, because my training data, if you remember, are at the object level. I have a ground truth bounding box, the red bounding box, for each object. I don't have training data per anchor. So what I have here is a situation such as this. I have, let's say, an image, which is my well-known sort of pedestrian over here. I have a ground truth bounding box, tight bounding box called BGT. And I have over here one of the many locations where anchors are present. So I am going to, that's one anchor. That's another anchor. That's another anchor, let's say. And the 3 is enough. As I said, behind an anchor, there could be a proposal. An anchor has fixed box sizes, right? But the proposal could be a regression that could be resulting to any shape. Still rectangular, but of any shape and size. Doesn't have to be the specific aspect ratio, the proposal, the specific sort of scale. So I am training, if you like, an RPN to do 2 things. One is to classify whether an anchor has an object behind it, any object of any class, or it's just background. And B, give me the proposal coordinates, because that's what I'm going to send to the second stage for evaluation in any case. As I said, in order for me to do that, I need training data, but which means that I need binary classification data. Behind its anchor, I need to have a label whether there's an object or not in terms of ground truth. And how can I get this if I have only this bounding box? This is what I'm discussing right now. So I'm suggesting the following. I'm defining. So the headline is training per anchor. Training dataset generation for RPN. This is what I'm discussing. This is the title for the RPN specifically. So we define a TP of 0.75, which, as you know, the T is the IOU threshold, that has a TN of 0.3. And for each anchor, when the IOU of the anchor box is greater than TP, then anchor is positive. There is indeed a box, and there is indeed an object behind it. Okay. So when this guy is going to be positive, potentially. These two guys are going to be negative. Therefore, now I have labels at the anchor level. So I have now this guy is going to be positive. This guy is going to be negative because it has zero IOU with the ground truth bounding box. Of course, these guys will be negative too. The others that are between the TP and the TN, I'm just ignoring. Okay, or we'll do something else. I can't remember now from the engineering of the paper. But let me write down also that for IOU less than TN, anchor is negative. The neutrals we can throw away. So I now have the binary classifier for background versus object, any object again. And I also have I need to build a regressor that will give me the final coordinates of my proposal. Therefore, I need a loss function to do that. For the RPN, the loss is a composite loss. Not only I need to come up with a good proposals in terms of coordinate size and shape, but I also need to make sure that there's indeed an object behind it and not background, okay? So the composite loss is exactly the same loss as we have seen many, many times. This is definitely a binary cross-entropy loss that is taking care of the object versus background plus lambda summation over y sub k. L, we call it the Huber loss, which is, as I told you, the corrected for differentiability kind of purposes mean absolute error, the absolute function. So everything I have done for the training kind of dataset generation, everything I have done is to obtain this. I never had y sub k as an information. I only had at the ground truth level a red box. The presence of the y sub k over there, which I also got via this kind of comparison, is indeed important because I don't want to penalize the total loss if I don't have positive anchors. After all, only for positive anchors, I'm spitting out proposals. For the negative anchors, I don't. So when the y sub k is 0, this thing goes away. So I'm training this. So this is for our, so let me write it down. Only positive anchors are penalized for regression. Object versus background. Believe it or not, this was basically the RPN. Right? This is just the proposal kind of generator. Everything else is remaining the same as we have seen in the second stage, where the fully connected kind of layers determine for each of these kind of proposals based on features now that are being extracted at the proposal level, right? Determine whether the specific class now is present and what is the specific regression coefficients, in other words, the X, Y, W, and H of the predicted bounding box. Okay. I know it's a little bit of a strange kind of trajectory, and it's a lot of log diagrams and stuff like that, right? But what I want you to keep out of this discussion and this kind of object detections is read the papers, even if it's just for the last version, the faster kind of our CNN, just to appreciate the engineering kind of side. Okay, there are lots of details that we have skipped, right? There is code that is coming in. Now this code is being actively recorded from earlier versions of Keras in your website. So this code is specifically for, it's still in draft form. I have to review what happened. But basically there is a COCO data set which is being created over here. There is the RPN kind of code. There is the ROI heads, which are basically the second kind of stage determination. And of course, there's a training loop and what happens in the inference with non-max suppression, right? So I don't give promises these days, but I will try my best to vet the code and release it, right? To tell you that during the weekend. But from what I have seen, the code is very reasonable, okay? And it's PyTorch code. Okay? Obviously, if you want the absolute kind of ground truth outside of the scope of this specific kind of site, you can always go to Torch Vision, where in fact there is a faster CNN implementation. And when you step through the code, you go in with a debugger, and it will take you through the internals of their implementation there, right? Either of the two is sufficient for you to understand the full extent. Any questions on the object detection side? Yes, go ahead.
Where can we find the research papers?
The research papers are linked over here. Just click on the thing and you should be okay. There is also another paper, which is a paper that it is called 20 years of object detection, 20 years of object detection. So it gives you a historical perspective of what's really happening. I can't remember the full title. It's also linked on your website. It walks you through the two-stage, the one that we did right now, but also will give you some more historical perspective of what happens in the single stage. It's not a very recent paper. It's like 5 years old now, but it's a good paper to just get a historical perspective. In general, you're doing quite a lot of experimentation. So what I'm going to do now for this subsequent kind of time is I'm going to start what naturally flows out of this object detection, and this also has to do with your assignment 3, right? Which is basically called object tracking, right? Where now let's say we have a stream of JSON bounding boxes, and obviously, as I told you before, some of these bounding boxes say that I am not here while I am, and in the next frame they find me again. Okay, so they're making mistakes. And also, as I'm going behind occlusions, there's no perception information. There are no bounding boxes. As I'm coming out of the occlusion, yet they're starting to come again. And therefore, the task there is how to track, let's say, drones, which are moving in some kind of space, going in behind trees or whatever. So drone tracking is going to be your assignment. So we'll see how that goes. Okay, so this is basically, I finished earlier than I was planning. So I'm going to go a little bit slow on what's called probabilistic reasoning over time. So if I ask you what will actually be what would you include in a vector called the kinematic state of a car? What would you include? Kinematic state. Question. Direction. So definitely we will include velocity, maybe acceleration, right? V dot. That's common in physics, I think, if you remember. And then some kind of a location. Now location will do X, Y, Z, but obviously we need some other degrees of freedom. We'll have three-dimensional kind of masses, like the pitch, the roll, and the yaw, like 6 degrees of freedom just for what's called a pose. Anyway, you can include many things. Velocity is also a vector, so you can extract out of this direction, like that. So the concept of a state is definitely something we've seen in lecture number 1. And in fact, lecture number 1, we have seen a block diagram that allows us to suggest here that at the end of the day, our job is to come up in this kind of block which we are discussing today with some kind of estimate of S hat of the state, the full knowledge of which we will never get to know, because this is kept in the environment. And this state will, as a concept, will survive until the reinforcement learning days, which will be very sad days at the end of the course. But the block over here, definitely, in order for it to estimate this kind of state, it cannot do the one-shot processing that the object detector is doing only, right? Of course, there are object detectors who are doing more than one-shot processing. In other words, it doesn't process memoryless a frame, but it has to observe information over time, over a number of frames, over a number. And so in this respect, we need to have memory, right? We need to remember things, right? And so from that kind of perspective, we are going to do this. We are always going to decorate the state with T. In fact, we are going to be building a whole family. This family is called recursive state estimators. All RSC. And this recursive state estimator is a very general structure that is based on a pretty foundational kind of principle. In many instances in lecture 2, or even 1, when we looked at regression, I told you I'm imposing a specific probabilistic model called a linear model to predict the house price. Okay. Later on, we replaced that linear model with a neural network that was also doing prediction of house price without necessarily me sitting here and imposing the probabilistic model, and then the very general hypothesis space afforded by a block diagram of dense layers, concatenated dense layers. Similar situation is going to happen now in a sense that we have two choices. One choice is to come up with an estimator who is going to be fairly constrained by us in terms of its logic. And a second scenario is that let's bring in a neural network to do the same thing. Okay. Now, there are some important trade-offs between the two in now, because in many instances, this constrained version, which we'll discuss in today, is going to be very quick, very efficient. Behind it, there's going to be a reasoning kind of a block called a Bayesian reasoner. So there will be a Bayes rule somewhere in this construction. While in the case of neural network, we have no idea what the neural network will do, whatever it will do, right? The neural network, having said that, has the ability to cover this specific kind of situation. But here we are injecting domain knowledge. In other words, we are making this fast and quick relative to the neural network because we are injecting specific assumptions, right? So it's more vertical, but faster. Whether it is more accurate across many other variables that we may tune, who knows? Okay, it depends on the application. So I am going to introduce now, so this is number 1, which is basically the state. So I'm going to treat this as a random variable, which it is, obviously. And I'm going to introduce now the second random variable called action. This action, I will symbolize it with AT, is sometimes in many use cases is explicit, like I have a robot move, it moves, takes an action to move forward. And sometimes it is implicit. Well, I have a pedestrian who just decided to go left. You know, I have no control of the actions that the agent is able to do. Sometimes I do because I have the robot and I'm implementing the robot. Sometimes I don't. In our case, whether the drone move to the right or to the left or whatever, we have no control of. It's an implicit action, but we have to accept its presence because the actions are inducing state transitions. So we will definitely symbolize also actions with this AT1 colon T2. You're probably familiar with the slicing operation in Python. However, in this kind of domain, people grew up with MATLAB, another language that some of you may be familiar with. And in the MATLAB notation, T2 is inclusive. So this one means the set of actions from T1 to T2 inclusive. Sometimes these nuances are quite important to understand what's happening and to justify equations that we will write a bit later. Okay. The third variable is called measurement. GT. And the measurements are measurements which are coming to us from a variety of sensors. Could be a camera sensor, could be a LiDAR sensor, could be whatever. Okay? Or could be a combination of both. The measurements for our domain over here will be the object detector output. But obviously, measurements may stop and not coming because I went behind the desk over here. So I'm now in occlusion, I have no measurements. But guess what? I may continue to act in the app and no one knows. I mean, I may be continuing to act. A drone will leave the frame, the field of view of the frame. Obviously, the drone is not shot down at that time, but it may come back from another side of the frame soon after that. Right? So the problem is, so in computer vision, you have to sometimes go between this and this, in a sense that there is the state is in our domain is going to be hidden. We are receiving the measurements, but the measurements themselves are noisy, and the state is hidden. So we are titling these problems hidden state problems, right? So we have observed random variables and unobserved random variables. So we are going now to, again, we are adopting ZT1 colon T2 for this kind of reasons. And we are going to define probabilistic models. The first one I will define, and I'll close with that one. It's called the state transition model. And it is defined as P of ST. I'm not going to write P model. Everyone knows it's a P model, but I'll just write as P, ST, S0 to T minus 1, comma, A from 1 to T, comma, Z from 1 to T minus 1. So, as you can see here, a horrible conditional probability distribution. Completely horrible one, because I'm suggesting that there is a probability distribution that models which state I am going next, given a history of previous states I've been, a history of previous actions I have taken, and a history of previous measurements. And I'm writing this kind of equation like this because behind this equation there is an assumption, an important assumption, which I'm making. I want to call it not an assumption, but a convention. The convention is that first I'm acting, and then I'm going to receiving a measurement. So that kind of sequential order of things, right? If you do exactly the opposite, first you receive the measurement and then you act, you arrive at exactly the same formulation, right? But the indices will matter, if they will be different. And so for my notes, the convention also followed by Sebastian Thrun is first you act, then you measure. I will close here, and then I'll make in the next lecture another assumption that will allow us to simplify this horrible probability distribution to something much simpler. And of course, I will continue the lecture from that point onward. Okay, I need my sign-in sheet right now. Please go ahead and sign if you have it. Okay, thank you.
Is it like the Markov chain? Like
Markov model, hidden Markov model.
so when we're saying that the current at time t is equal to like probability, like the probability function of state t given previous states, and why are we considering the action that is in current frame as well, and not the previous, only until the previous one?
We are there is a probabilistic graphical model that indeed brings the current action into the current state.
Okay, so it's not unlike
it's going to bring. I'm going to explain it next time.
the current action is also the current state is.
It is the current action who induces a state transition from ST minus 1 to ST. Where What is it?
Professor, so we can print out the all three, right? For